Anyone who's fascinated by the cutting edge of technology, especially in the realm of security, can't ignore the revolutionary potential of quantum computers. These aren't just faster versions of the laptops we use every day. They're machines that operate on principles of quantum mechanics, allowing them to solve problems in seconds that would take traditional supercomputers billions of years. Imagine a device so powerful it could unravel the most complex codes underpinning our digital world, from banking transactions to national defense secrets. That's why agencies like the FBI, the CIA, and governments around the globe are monitoring developments in quantum computing with intense scrutiny. But what if some of the most groundbreaking work is happening right under our noses, shielded behind the facade of a tech giant like Microsoft? Recent announcements suggest that Microsoft's quantum efforts extend far beyond what's publicly visible, potentially involving advanced facilities and technologies that could redefine global power dynamics. Today, we're embarking on an in-depth exploration of the rumors and realities surrounding Microsoft's quantum initiatives, what they've achieved, why it matters on a geopolitical scale, and how it could transform not just scientific research, but cybersecurity, artificial intelligence, and the fabric of your everyday life. Stick with us through this journey. By the end, you'll see why quantum computing isn't a distant dream, but an imminent reality that demands your attention. Microsoft's publicly acknowledged quantum facilities have been making waves for years, showcasing innovations that push the boundaries of what's possible in computing. Station Q, located at the University of California, Santa Barbara, has long been a hub for theoretical and experimental quantum research, collaborating with leading physicists to explore exotic quantum states. In Redmond, Washington, Microsoft's quantum group focuses on integrating quantum hardware with software ecosystems, developing tools that could one day make quantum computing accessible via the cloud. Across the Atlantic, their facility in Lyngby, Denmark, has been instrumental in hardware development, housing labs equipped for cryogenic experiments essential to quantum operations. And just this month, on September 17th, 2025, Microsoft announced the opening of a new quantum research center at the University of Maryland's Discovery District in College Park, Maryland. This expansion positions Maryland as a burgeoning hub for quantum innovation, leveraging the state's academic resources and proximity to federal agencies. But here's where things get intriguing. While these centers grab headlines with breakthroughs like the Majorana 1 processor unveiled in February 2025, whispers persist that they might only represent the tip of the iceberg. If Microsoft is indeed mastering unbreakable cryptography through quantum means, does that give them unparalleled influence over the digital realm? The implications are staggering. In a world where data is the new oil, controlling the tools to protect or crack, it could shift the balance of power overnight. As we peel back the layers, consider this. The race to quantum supremacy isn't just about speed. It's about who holds the keys to tomorrow's security. Governments and corporations alike are investing billions because the first to cross that finish line could decrypt encrypted data harvested today, exposing secrets from years past. DARPA's deep involvement, including their selection of Microsoft for the final stage of the US-2 QC program in February 2025, underscores that this isn't mere academic curiosity, it's a matter of national security. The retracted Majorana particle claim from 2021, followed by a period of relative silence until the 2025 breakthrough, fuels speculation about hidden progress. What advancements were made in those intervening years, and why the veil of secrecy around a technology poised to upend global power structures? As we dive deeper, you'll uncover clues that suggest Microsoft's quantum story is far more complex than press releases let on. While Microsoft's visible quantum hubs dominate the news cycle, a closer examination reveals a trail of evidence pointing to potentially undisclosed operations. Take their patent filings, for instance. Microsoft has amassed over 546 quantum-related patents globally as of March 2025, belonging to 178 unique patent families. These aren't vague ideas. They detail sophisticated technologies that go well beyond conventional computing. One recent patent focuses on Bayesian tuning of quantum gates to minimize errors, enhancing the reliability of quantum operations in noisy environments. Another describes methods for fault-tolerant quantum cloud integration, allowing seamless scaling of quantum resources over distributed networks. Then there are patents on quantum teleportation channels, which could enable instantaneous data transfer across vast distances without interception, and topological quantum error correction, a cornerstone of stable qubit designs. These filings hint at quantum networking protocols that might form the foundation of an entirely unhackable internet, impervious to eavesdropping due to the principles of quantum entanglement. Even more provocative are patents combining quantum computing with AI, such as quantum-enhanced neural networks that process information in parallel universes of probability, potentially revolutionizing machine learning by solving optimization problems exponentially faster. Patents like these are more than legal protections. They're breadcrumbs leading to advanced R&D that Microsoft guards closely. Why patent such cutting-edge concepts now unless substantial progress has already been achieved? The disparity between the retracted 2021 Majorana discovery, where experimental errors led to a public pullback, and the triumphant reveal of the Majorana one in February 2025 leaves a 3-year gap ripe for conjecture. During that time, was work continuing in shadowed facilities, away from prying eyes? Public labs might serve as showcases for vetted achievements, while the real leaps occur elsewhere, perhaps in fortified sections of existing campuses or entirely new sites. The new Maryland Center, with its emphasis on scalable quantum computing, could be part of this expansion. But satellite imagery of the Redmond campus reveals windowless buildings with heavy electromagnetic shielding, ideal for sensitive quantum experiments that require isolation from external interference. In Denmark, the Lyngby facility boasts rooftop setups resembling industrial cryogenic systems necessary for maintaining the near absolute zero temperatures quantum chips demand. These aren't standard office features. They're hallmarks of high-stakes research. What do you think is brewing behind those secured doors? Share your theories in the comments. We'll circle back to some of the wildest ones later in this video. As we connect these dots, it becomes clear that Microsoft's quantum pursuits are layered with intrigue, blending public innovation with hints of concealed mastery. Delving into the facilities themselves through satellite sleuthing and public records paints a picture of infrastructure built for extraordinary purposes. Microsoft's Redmond headquarters, sprawling across a vast campus, includes structures that deviate from typical corporate architecture. High-resolution imagery shows buildings with reinforced exteriors, minimal windows, and extensive HVAC systems suggestive of dilution refrigerators. Devices that cool quantum systems to millikelvin temperatures, colder than the vacuum of space. These setups are energy-intensive and expensive, far exceeding what's needed for routine software development. Similarly, the Lyngby Center in Denmark features massive cooling towers and power substations consistent with running multiple quantum processors simultaneously. Quantum computers aren't plug-and-play. They demand specialized environments to shield fragile qubits from cosmic rays, thermal noise, and even the Earth's magnetic field. The scale observed implies capacity for experiments beyond the publicized ones. Station Q at UC Santa Barbara, founded in collaboration with academic partners, emphasizes theoretical foundations, but includes clean rooms for nanofabrication of quantum devices. And now the freshly announced Maryland facility promises to accelerate scalable quantum tech, potentially integrating with nearby government resources in the DC area. This strategic location isn't coincidental. Proximity to agencies like DARPA and the NSA facilitates classified collaborations. But the buildings are just the shell. The real story lies in the timeline of Microsoft's quantum journey, which harbors enigmatic pauses. Back in 2018, Microsoft touted a breakthrough in observing Majorana particles, quasi-particles that could form the basis of robust qubits. Excitement built until 2021, when the claim was retracted amid scrutiny over data inconsistencies, leading to a corrected study that reignited debates as recently as August 2025. What followed was a hush with limited updates until the Majorana 1 announcement in early 2025. This leap from setback to success in roughly 4 years suggests relentless, possibly covert development. Experts speculate that undisclosed labs bridge this gap, refining nanowire technologies and error correction protocols away from academic peer review. The patents filed during this period, covering everything from quantum gate optimization to hybrid quantum classical systems, support this narrative. With DARPA's funding pouring in through programs like US2QC, where Microsoft advanced to the validation and co-design stage alongside PsiQuantum, the military angle sharpens the focus. This isn't hobbyist tinkering, it's a high-stakes endeavor with implications for defense and beyond. If you're as captivated by these revelations as we are, smash that subscribe button now. We're committed to uncovering the stories mainstream outlets overlook, and your support keeps us digging deeper. Microsoft's quantum endeavors transcend pure science, positioning the company at the epicenter of a burgeoning global arms race in technology. In February 2025, DARPA announced Microsoft's selection as one of 2 finalists in the US2QC program, aimed at developing utility-scale quantum computers capable of solving real-world problems beyond classical limits. This partnership injects millions in funding and access to defense expertise, but it also raises questions about classified extensions. If DARPA is publicly endorsing Microsoft's topological qubit approach, what undisclosed contracts might be accelerating progress? Defense experts highlight that these qubits could transform military applications, from optimizing logistics for drone swarms to breaking enemy codes in real time. We're approaching what insiders term Q-Day, or Quantum Day Zero, the pivotal moment when a quantum machine shatters RSA encryption, the linchpin of modern cybersecurity. When that arrives, the entity wielding such power could access fortified networks, exposing sensitive data worldwide. Microsoft has openly discussed the Harvest Now, Decrypt Later threat, where adversaries like state-sponsored hackers amass encrypted data today, awaiting quantum tools to unlock it tomorrow. This isn't paranoia, it's a documented strategy. Your online banking, health records, and even government dispatches rely on encryption vulnerable to quantum attacks. A sufficiently advanced quantum computer could breach these in moments, potentially causing economic turmoil or intelligence catastrophes. To counter this, Microsoft launched its Quantum Safe program in August 2025, focusing on post-quantum cryptography to fortify products like Azure and Windows against future threats. They're not alone in this race. Competitors like Google and IBM pursue different qubit technologies, but Microsoft's emphasis on stability gives them an edge. Geopolitically, nations are mobilizing. China has poured billions into quantum initiatives, aiming for supremacy in quantum communication and sensing. Europe's quantum flagship program coordinates continent-wide efforts, while the US leverages public-private partnerships like Microsoft's. The victor doesn't merely earn Nobel Prizes, they gain the capacity to peer into encrypted communications, safeguard their own infrastructure with quantum keys, and potentially dominate critical sectors like finance and energy. Microsoft's Majorana One, with its reported low error rates and scalability path to millions of qubits, signals that practical quantum computing could emerge in years, not decades, accelerating this timeline. As we explore further, envision a world where quantum superiority dictates alliances and conflicts. It's closer than you think. Beyond the realm of defense, Microsoft's quantum research unlocks possibilities that blur the line between science fiction and tangible reality, grounded in established physics. Consider quantum-enhanced AI agents. Current models like GPT series consume vast energy for training, but integrating quantum processors could enable learning through superposition, evaluating countless scenarios simultaneously. This hybrid approach, hinted at in Microsoft's patents, might birth AI that's not just faster but intuitively smarter, solving intractable problems in drug discovery or climate modeling. What if Microsoft's labs are already prototyping these systems, rendering today's AI obsolete? Then there's quantum sensing, an underappreciated gem. These devices detect infinitesimal changes in gravity or magnetic fields, enabling GPS-independent navigation, subterranean mapping, or spotting hidden threats like stealth submarines. In military contexts, quantum radar could unmask invisible aircraft, revolutionizing warfare. Equally transformative is quantum communication, leveraging entanglement for secure channels where interception collapses the signal, making hacks impossible. Microsoft's work on quantum networking protocols could underpin a global, tamper-proof internet. These applications explain the premium on secrecy. Topological qubits' inherent stability makes them ideal for real-world deployment, unlike fragile alternatives. The timeline gaps from the 2021 retraction to 2025's Majorana 1 align with a shift toward these practical uses. But the darker side looms. If one entity monopolizes such tech, they could control digital society. This isn't abstract. It's the crux of our quantum future. The human stakes of quantum supremacy are profound, touching every aspect of daily existence in ways that demand preparation now. Financial systems, built on encryption like AES and RSA, face existential risks. A quantum breakthrough could decrypt transactions en masse, eroding trust and sparking market crashes worth trillions. Personal privacy evaporates. Encrypted emails, photos, and passwords from years ago become readable, exposing lives to identity theft or blackmail. Even scarier, harvest now, decrypt later, means data collected today by foes could reveal historical secrets, from corporate strategies to personal affairs. Militarily, nuclear controls, satellite links, and command chains rely on secure comms. Quantum cracks could destabilize superpowers, altering global equilibria. DARPA's investment in Microsoft underscores this as a survival imperative. Microsoft's push for quantum readiness in 2025, urging businesses to adopt post-quantum strategies, acknowledges the urgency. Yet who sets these new standards? If Microsoft leads, do they dictate access? This narrative isn't Microsoft versus rivals. It's about equitable stewardship of world-altering tech. To ground this, let's examine Microsoft's disclosed quantum ecosystem. Station Q, under Michael Friedman's guidance, merges computer science with quantum physics. The Redmond Quantum Group, led by Krista Svor, crafts algorithms for future machines. Copenhagen's labs drive hardware, while Maryland's new center scales efforts. The Majorana one stands out. Unlike fragile superconducting qubits, it uses topological ones from Majorana fermions in indium arsenide aluminum nanowires, shaped like an H for stability. This reduces error correction needs, paving to millions of qubits versus today's hundreds. Public showcases mass deeper work, per patents and DARPA ties. In conclusion, quantum computing heralds a paradigm shift, with Microsoft's approach potentially leading. From retracted claims to 2025 triumphs, the shadow of hidden progress looms. If this unsettles you, subscribe. Our next deep dive awaits.